So today on the podcast, we're covering a Jacobsen paper where they build these chiral beta-beta difluoroalkyl bromides from alpha bromostyrenes. And this reaction is really neat because it installs a gem-difluoromethylene group with a stereocenter alpha to this group. And this gem-difluoromethylene group is really key because it's installing these carbon-fluorine bonds that are very prominent in medicinal chemistry, agrochemistry, and materials chemistry. But if you look at the numbers of compounds that use them in these industries, there is a large gap between the industrial uses of these carbon fluorine bonds and what is available and what is found in nature. And this is partly due to the lack of fluorine molecules in the chiral pool, meaning that these are just chiral molecules that are available and very cheap and very abundant, such as amino acids and terpenes. And so Jacobsen's goal of this paper was to develop a new method to access a molecule that mimics something you would find in the chiral pool with this gem-difluoromethylene unit.
And just to expand on what you were saying a little bit, Grace, the paper, like you said, makes the claim that there are very few fluorine-containing natural products in the chiral pool, but even beyond that, there are very few fluorine-containing natural products, period. And this isn't because fluorine is not an abundant element on Earth. It's actually the most abundant halogen on Earth. But it makes sense if you think about some of the chemical properties of fluorine, which is that it's naturally occurring in mostly insoluble salts, which makes it difficult to deliver into aqueous biological systems. And just other properties of fluorine, its high oxidation potential, make it hard to introduce in a biological system.
But as Grace previously mentioned, what has been found in the medicinal industry and in the pharmaceutical industries is that having a difluoromethylene group can be a bioisosteer for functional groups commonly found in natural products. So the paper has a nice kind of summary of this in their figure 1A, where they show that the dipole of this gem-difluoride is similar to that of both an ether and a ketone. And the bond angle around that carbon matches similar to that of the ethers and to the ketones. And so by installing this functional group, you can gain metabolic stability by removing reducible or oxidizable functionality that is in a molecule. And typically you can also gain some solubility properties by adding in fluorines to these natural products. So this becomes a really nice methods that allow us to install readily this style of a gem difluoride into these natural products through different means and through different functional handles are really useful and will potentially provide a means to access new, unique gem difluoros in kind of existing natural products.
And I think this is a really neat advance because this method again allows you to set a homobenzylic stereocenter that is able to go on to further functionalization. And if we look at other methods that are currently in the literature for installing these gem-difluoromethylene units, many of these methods epimerize those stereocenters. So if we look at the most widely used strategies for the addition of a gem-difluoromethylene group, most start from a prochiral electrophile, which can undergo a nucleophilic attack to form a carbon-carbon bond by using either a Grignard or an alkyne or an alkene. But that requires you to have the gem-difluoro group already installed into your electrophilic group. Another strategy that has been used is doing a deoxyfluorination of ketones or aldehydes using a nucleophilic fluorinating reagent such as DAST. And in this pathway, any stereocenter alpha to the gem-difluoromethylene group is often epimerized, or it can undergo a rearrangement reaction if that's a tertiary center, or can undergo other decomposition pathways. And so this method, while it is widely accepted, if you have a stereocenter set at that position, will often be ablated or will undergo some sort of rearrangement or decomposition pathway. The third kind of general strategy for installing these groups requires you to use a masked fluorine source. And so some common ones are with sulfonyl difluoromethylation reagents or trimethylsilane methylation reagents. And in this case, you are able to install the mass CF2 group and control the stereochemistry alpha to that center, but you then have to go a subsequent step to remove and unmask your methylene unit.
Yeah, one other kind of isolated method that I found that I thought was pretty cool and wanted to bring up was a JAX paper that was published last year, where they show that malonic acid derivatives can be converted into these fluoromethylene groups. So basically you have a geminal dicarboxylic acid that in the presence of a silver oxidant, which can oxidize that carboxylic acid to the corresponding carbon radical. The carbon radical then reacts with select fluor, and you can get to the difluorinated product that way. So basically just exchanging a geminal dicarboxylic acid with a geminal difluoroalkane.
So we were all really interested in this method, particularly for the gem-difluorination and for installing the stereocenter, but really the catalytic cycle intrigued us, and we wanted to learn more about these chiral iodinanes and how they work and how they function, and we thought that would be a really fun topic to discuss and just learn more about.
Yeah, so before we jump right into the chiral hypervalent iodine catalysts, just a little bit of an introduction on the achiral hypervalent iodines. At least when I usually think of these, I usually think of them either as oxidants. So IBX, for instance, is a really common hypervalent iodine oxidant. Same with desmartin priodinane. And those are usually iodine 5 reagents. But there are also iodine 3 reagents, and a lot of those do group transfer type reactions. So both of these are oxidative processes, but they can do some different things.
So one of the reasons people are interested in using, or got kind of interested in using iodines, I guess, and we should point out that hypervalent iodine and iodine are basically interchangeable when you're referring to these compounds, is that they're friendly oxidants. They're typically non-toxic, they're air stable, they're reasonably easy to handle, and a lot of times isolatable. Some of the like fluoroiodines or oxoiodines that we'll talk a little bit more about today have been isolated and then used stoichiometrically in either racemic or asymmetric transformations. And so they're relatively easy to handle. And so when you think about wanting to do an asymmetric oxidation, being able to use an oxidant that you can kind of just prepare and weigh out or make in situ, like in this case through the use of MCPBA, it makes it really nice. And so kind of just thinking about iodine catalysis, the cycle that you can kind of think of when you're thinking about that is an I1, I3 catalytic cycle where you oxidize I1 to I3 and then through some transformation go back down to I1, most likely, as Matt said, through a group transfer style reaction. Before catalysis, the interest in using chiral iodines to enact some sort of enantioselective transformation started basically with doing the group transfer of oxygen to sulfur. So trying to make a chiral sulfoxide from a aryl sulfide. And so this work was pioneered by Kita in the late 80s to early 90s, getting up. And the way that they basically did that is they prepared aryl iodide species and used arenes from the chiral pool to generate these iodines that they would then make into these stoichiometric oxidants and then do a group transfer of oxygen to make an aryl sulfoxide. And they could get EEs up to about 72%, which is pretty good. But the key with that reaction was it was stoichiometric in the iodine. And so they prepare the iodine, then add it and run the reaction. There are a bunch of these different stoichiometric reactions. I think the most pertinent to the reaction today was there was a dioxytosylation reaction that was developed by Wirth in 2001, basically using similar iodoarenes to what we are using now, or what Jacobsen has used for this reaction as well. And basically what they did is they did a 1,2 dioxytosylation of styrene. So one of like the first examples of doing one of these kind of difunctionalizations of styrenes. So continuing forward, Wirth went on to develop a catalytic method for this dioxytosylation using a chiral iodine. Just recently in 2020, the same group from Wirth developed an acetoxylation that uses a more recently developed iodoarene style chiral catalyst. And this family of iodoarene catalysts has kind of become the workhorse family of functionalization catalysis. And so these chiral iodoarenes were developed by Ishihara in 2009. They're based on resorcinol, which is an arene ring that has a 1,3 diol substitution pattern. And then the iodine atom is stuck in between the two of them. So it's basically a 1,3 diol with the two positions substituted by iodine. And then off of the diol, each of those oxygens can be functionalized with chiral functional groups. These typically end up being kind of methylenes to some sort of carbonyls that are then further functionalized. You can kind of stick pretty big groups on here. You can expand it. They're very modular. And so it's allowed this family of catalysts to be really well developed into a large group of catalysts.
So the Jacobsen group has leveraged this type of catalyst to do a variety of different transformations, including the one in this paper today. And so looking at the catalytic cycle of how these iodoarenes catalyze reactions and catalyze this functionalization, they start by being oxidized by MCPBA to the iodosyl arene, which then is followed by deoxyfluorination with a HF source. And this catalyst is activated then to coordinate your alkene to form an iodonium-like intermediate, which then undergoes the enantiodetermining step in the reaction, which is this fluoroiodination of the alkene, forming this alkyl iodinane.
So this alkyl iodine is a common intermediate for a number of these functionalization reactions that are catalyzed by these chiral iodine catalysts. But this first step which you could kind of consider turning over the catalytic cycle, which is this oxidation of the aryl iodide by MCPBA. Basically, it's an oxidation to an iodosyl arene. That's basically just the iodide now doubly bonded to an oxygen. And then it goes through what is most likely a sequential attack, protonation, and loss of water by HF. And so you end up with what is now your iodoarene, your difluoroiodane catalyst, which has now your two fluorides bound to your iodine. And now you're in that I3 active state to then be able to coordinate to that alkene and go forward.
So like Grace and Wes alluded to, this catalytic cycle is very similar to the one that Jacobsen has proposed in several of his previous papers. So there's a 2016 JAX paper, a 2016 Science paper, and a 2018 JAX paper that are all doing a very similar thing. So this oxidation to the active hypervalent iodine species is the same. And then there's a coordination of some kind of alkene. The paper that we're looking at is specifically a vinyl bromide, but in the other papers, it's some kind of alkene. And in all of the papers, you get this enantiodetermining fluoride attack onto the alkene to form an alkyl iodane. The step after this alkyl iodane intermediate is what differentiates the 4 papers that I was referring to, this one and then the 3 previous ones, to get to different products. And basically what you notice, the common trend here is the iodine species is a really, really good leaving group in the alkyl iodane intermediate. So almost any kind of nucleophile, whether that's intermolecular or intramolecular, can attack that carbon iodine bond and displace the iodine species. So I think it's helpful to actually look at all of these previous publications to see how the authors of the paper that we're covering now thought of this idea and got to the idea that they're at. So in terms of the 2016 JAX paper, they got to this alkyl iodane intermediate, and then with all of the other HF around, the fluoride acted as a nucleophile and what's kind of like an SN2 reaction to stereospecifically displace the iodine species at the carbon. So fluoride attacks at the carbon to displace that leaving group. And what that gives you is a 1,2 difluorinated product.
So the Jacobsen group noticed in a few of their substrates that they were getting the opposite diastereoselectivity for the 1,2 difluorination reaction. And they pitched that this came from this ankymeric assistance effect, where when they had nucleophilic functional groups that could displace the iodoarene from the carbon that it was on, they would form a cyclic ring structure, one of them being an oxyraminium ion. And then once that had formed, you would get displacement of the three-membered ring by external fluoride to give you the 1,2 difluorinated product with the opposite diastereoselectivity, selectivity, since you basically did now 2 SN2 reactions rather than 1 SN2 to displace the iodoarene. What's unique about this is this idea of forming these cyclic structures, basically displacing the iodoarene and forming some sort of cyclic intermediate is not uncommon for these catalytic cycles. In fact, the 2016 paper that was published by Jacobsen used the phenyl group of the styrene to form a phenonium ion intermediate, and that was what led to them being able to do 1,1 difluorination rather than 1,2 difluorination, where once they formed that phenonium ion, again, external fluoride would be able to attack, but this time it attacked at the fluoride carbon, at the pre-functionalized fluorocarbon, to give you this 1,1 difluorination. Furthermore, the group of Killy and Moonins has also seen similar reactivity when they looked at doing 1,2 diamination reactions. And so similar to what was pitched for kind of the ankymeric effect for some of the iodoarenes done by Jacobsen, once you formed the alkyl iodane intermediate, the first added amine would collapse down, forming an aziridinium intermediate. So another one of these three-membered cationic rings that would then be displaced by another external amine, leading to 1,2 difunctionalization enantioselectively. And so I think it just comes across, what's really interesting about these catalytic cycles that have been pitched by Jacobsen is that once you get these iodane catalysts to add across that alkene, the subsequent reactivity can be fairly well understood to basically go from this enantioselective addition across the alkene to an enantiospecific displacement, allowing you to generate these enantiopure materials.
Transitioning back to this paper, after looking at all of the precedent, basically they've shown that a number of different pendant nucleophiles, Wes mentioned, amines, as well as even arenes, can displace the iodane leaving group. The real new idea in this paper is, instead of using those pendant nucleophiles, to use a bromine. So in this paper, a bromine acts as a nucleophile, displaces the iodane to get to a bromonium intermediate, and then fluoride anion in the solution can do a stereospecific nucleophilic attack to open the bromonium intermediate to get to the difluoroalkyl bromide product.
So they next started their catalyst optimization using an optimal catalyst that they had found in previous work for other alkene fluorofunctionalization reactions. And when they subjected this catalyst to the reaction conditions, they saw 100% conversion with 80% EE. So they got a really nice hit off the bat that they could then further optimize. So they tried a variety of different catalysts with different substitutions, but they noticed a correlation as they started to change the benzyl group on the catalyst. And they saw that as they increased sterics at this position, they saw an increase in EE. And when they plotted this versus the Charton parameters, which are just well-defined steric parameters, they were able to see that as they changed from methyl to ethyl up to tert-butyl, there was a good correlation with the delta G of the transition state, which is directly related to the enantiomeric ratio that they observe experimentally. After identifying this more sterically bulky benzyl group, they then decreased the catalyst loading from 20 mol% to 10 mol%, and they saw a decrease in both the conversion and the EE. And they had stated that when they tried to extend the reaction times, they were not able to make up for this lower conversion and lower EE. And additionally, when they ran the reaction without the iodoarene catalyst, they did not see any background reactivity. And so based on these pieces of evidence, they thought their catalyst was being deactivated in some way. And so they isolated and tried to recover their catalyst, and they found that one of the benzyl oxy groups was replaced by a monofluorinated derivative of their alpha bromostyrene substrate. And they hypothesized that this deactivation pathway of the catalyst might happen through accessing the bromonium ion, where the carbonyl of the ester can attack this intermediate and therefore form this deactivated catalyst. And so if this was happening through the nucleophilic attack of this benzyl ester group, they hypothesized that if they make this benzyl ester more electron deficient, then that would decrease the nucleophilicity of this group and therefore decrease the decomposition in the reaction. And so then they tried several electron deficient substituted benzyl esters, and they saw that when they para-substituted this group with an SF5 functional group, they were able to identify their optimal conditions, which were running this reaction at an 84% isolated yield with a 92% EE.
The Jacobsen group now has an optimized catalyst and they're ready to run a scope. The scope is reasonably good. They basically vary a lot of functionality off of that aryl group, which is really the main functional aspect of this catalyst. So they're able to kind of handle triflates and nitro groups, which are really exciting. Electron withdrawing works pretty well. I think they do note that electron donating groups do not handle this reactivity very well. They're able to have a halide on that group, which works nicely. Meta and para functionality is fine. And then they do show that they're able to have a heterocycle, so they can replace the aryl ring with a N-methylpyrazole as well and still get relatively good yields. But the enantioselectivity does drop off in that case. Most of their enantioselectivities throughout this stay okay. They are mainly in the 90s, but they do drop off in certain cases where you end up getting to some of the more electron donating groups as well. The scope is nice. It does show that there is some functionality here. But the more interesting aspect of this paper to me was that they show what they can do when you are able to leave a enantio-enriched homobenzylic bromide present on these molecules. And so through just 3 simple diversification reactions, they do an enantiospecific inversion with sodium azide. They do need to use pretty forcing conditions. They state that having the benzylic gem-difluorides does prevent that SN2 from being fairly reactive, but they're able to get 99% enantiospecificity for that inversion of that stereocenter through the azide addition. They go on to show that they can form, and again, in extremely high enantiospecificity, through an intramolecular SN2, they can form an epoxide from an alcohol and a thietane from a thiol. And so just these simple transformations show that from this reaction, you're able to diversify readily this benzyl gem-difluoride.
They finished this paper really trying to get at the origin of the enantioselectivity in this reaction. And this is where the collaboration, I'm guessing, with Matt Sigman really came into play, because Matt Sigman has this program of using linear regression techniques to understand the origin of enantioselectivity with the goal of designing new catalysts with better reactivity, better enantioselectivity. So we're not going to get into this really in depth, but the idea here is to, in this case, plot enantioselectivity on the y-axis and some parameter on the x-axis and look at a lot of different parameters that may be bond length, or like you were saying, Wes, NMR shift. In this case, they're looking at a cation pi interaction or a pi-pi interaction and just looking for a correlation that you can correlate some parameter with the substrate of the catalyst with the enantioselectivity of the reaction.
I really like how they went about this. So they start with just trying to see if they can find an experimental linear free energy relationship. And so they start by looking at the classic Hammett parameters, so the sigma para sigma meta values. These values are based on the dissociation of benzoic acids. And so, for a reaction like this, or for a catalyst like this, they don't directly correlate to, kind of what they're looking for, which is, kind of the electronic factors of these iodoarenes. But they see a modest correlation between the Hammett parameters and the enantioselectivity of this reaction. What they basically state is that The sigma metaparameter in particular is kind of well known for correlating to the strength of non-covalent interactions. So these pi-pi interactions, or these CH-pi interactions that Matt was kind of talking about. So they go further into delving into, trying to kind of go after some of these more multivariant regression analyses that Matt Sigman is known for, using kind of DFT calculated parameters. But they basically say that when they try into kind of two-variate or some of these multivariate models, they really don't get good correlations. What I really, really appreciate is they recognize that, you can always add more and more variables into an equation, and eventually it might fit. But that really doesn't tell you anything. And so they kind of stopped and went, well, okay, let's see if we can simplify everything a little bit more. And they focused solely on single variable kind of thoughts that they could evaluate. And so that's where they kind of developed the symmetry adapted perturbation reaction, where they truncated, kind of the iodoarene, and they truncated their molecule down to just kind of the most important interactions that they thought, which would be the CH interaction and this pi-pi interaction. So when they run these analyses, they started with looking at this CH pi interaction, where the probe molecule, so basically they truncated the bromoarene down to literally just benzene, and looked at the truncated iodoarene molecule, where they really just focused on the benzyl R1 kind of arene parameter. And what they found is, as they varied the benzene CH pi interaction energy by varying substituents off of the iodoarene catalyst, they saw a pretty good linear correlation between that CH pi interaction energy and the experimental enantioselectivity. And what was nice is they were able to kind of use a training set, and then they predicted a couple of catalysts outside of that training set. And when they ran those reactions, the EE fell pretty well in line with the predicted enantioselectivity for that reaction. They did this as well with a pi-pi interaction. Again, looking at kind of this probe molecule versus the iodoarene overlap, that arene being the phenyl group that the iodide's actually attached to, that 1,3-diol that the iodide is attached to for the catalyst. The correlation there was not as strong, but they were looking at the LUMO energy of the substrate. In this case, they did still see a pretty good correlation, and again, for the most part, pretty well validated that training set. And so the conclusion of all of this comes down to figure 5C, where basically when you look at one arm of this C2 symmetric iodine catalyst, you have a pi-pi interaction between the 1,3-diol kind of core structure and the substrate arene phenyl group of the styrene. And from the meta proton on that styrene, a pi-CH interaction to one of the benzyl arenes off of the iodine catalyst. And so this positions basically the catalyst directly with only one face of that alkene of the styrene accessible to then be attacked by a fluoride from solution, leading to that enantioselective reaction.
So moving back out, thinking about the paper as a whole, I did like this paper. And I think one of the reasons I liked it is it's a great example of taking an idea, and the idea is, in this case, enantioselective fluorination of alkenes. And this idea that they had back in 2016, they've now leveraged it into several different papers that all provide useful and different molecules and all provide some interesting catalyst insights.
I also really enjoyed Matt Sigman's portion of this paper, and just talking about the correlations that they see within the catalyst and how to design a better catalyst to do the desired transformation.
The last thing I'll say is I really enjoyed learning about these chiral iodine catalysts. I have to admit, before reading this paper, I knew very little about them. And this is it's just an interesting catalyst class, I think, that I'm not used to thinking about when thinking about asymmetric catalysis.
And that's our show. Thanks for tuning into this episode of the Cyclo Edition. For more information on the papers discussed, we have included a selection of resources we used in our research at the end of the YouTube video. This was our take, very interesting paper, and we would love to hear from you. Please comment below the YouTube video and reach out on social media. You can follow the Cyclo Edition on Twitter, where we will post updates about our next episodes. If you enjoyed this episode, please like and subscribe.